Good morning, friends. Welcome to Synchronous Motor. Next topic, that is a continuation of performance of synchronous motors. Wish you happy Diwali today. So, recall what we have seen previous class. The previous class we have seen that what do you mean by the synchronous motor? We compared synchronous motor with existing well-known DC motors and induction motors. In construction point of view, we compared with all other motors, the stator and rotor. On a constructional point of view, we have seen and we have also known the working principle of synchronous motor, and we have seen the starting methods of synchronous motors, that may by using the mechanical input from outside by damper windings. In another class, we have seen analysis the performance of synchronous machine with considering no load conditions, with assuming losses are an ideal condition 0, losses are considered small amount of the losses to meet the inherent losses. And another case we have seen, if load increased on rotor, what are the changes takes place inside a motor. So we have seen with the help of phasor diagrams. Now let us see in a further class. Let us introduce myself, Dr. C.H. Yadaya, Senior Lecturer in Electrical and Electronics Engineering, Government Polytechnic, Osnabad. This topic regarding to 5th semester AC motors. Today topic is expression for back EMF. In previous periods, we have discussed the performance of synchronous motor on no load, synchronous motor on load, analysis of phasor diagram. Today objectives, on completion of the period, you would be able to know the derivation of back EMF in synchronous motor. Problems on back EMF equations. Now, as you know that the synchronous motor required dual supply. AC supply is given 3-phase AC supply is given to a distributed winding in stator, and DC supply is given to concentrated winding in rotor through slip rings. When 3-phase supply is given to stator, it produces a rotating magnetic field, constant rotating magnetic field, that is a 1.5 times of flux produced by each phase, 1.5 times of phi m magnitude, and rotating in air gap at a speed of synchronous speed, that is Ns is equal to 120 F by P. Now, due to this rotating magnetic field, damper windings on rotor pole shoes induces some flux, and these two flux interaction takes place. The motor works similar to three-phase induction motor. Once a rotor reaches its nearby synchronous speed, then DC supply is excited to the rotor. Rotor induces or establishes its own north pole and south pole and rotor poles, and stator north pole and south poles rotating in synchronous speed. Now rotor is also rotating in the same direction of stator magnetic field, and stator north pole, rotor south pole interlocked each other. Stator magnetic axis and rotor magnetic axis coincides, or some may be angle between the stator axis and rotor axis, that is a load angle alpha. During this period, the motor works at synchronous speed. Once rotor is rotating in synchronous speed, the relative speed, damper windings and stator field is 0, then induced EMF in the rotor damper windings 0, then it works now as a synchronous motor. During this period, due to the some alpha angle between the stator axis and rotor axis, the alpha decides how much armature current has to be drawn from three-phase input supply at the angle of phase power factor to develop small amount of the torque to meet inherent losses like friction and windage losses, iron losses, that may be eddy current loss and hysteresis losses, and somewhat copper losses in stator and rotor. We have discussed this previous class. At the same time, we analyzed IA is equal to armature current is equal to applied voltage V minus induced voltage back EMF V minus EB by ZS, where ZS is equal to synchronous impedance, that is a vector sum of RA plus J of XS. Now the voltage, applied voltage corresponding to the armature current, there is a phase angle power factor, that is a phi, and resultant of vector resultant of V applied voltage and induced back EMF in stator EB, it produces a resultant voltage that is called ER. This ER with respect to armature current, this angle is theta, we can say that is a internal angle. Now EB with respect to the reference, that is the alpha, we can say the coupling angle. So based on this one, we have drawn vector diagrams. Now let us see if the DC supply to the rotor injected to produce field poles on rotor. If injected voltage, DC voltage under normal condition, what will happen? If excitation is increased further, what will happen? If excitation is reduced from the normal value, what will happen? In this class, we will analyze. Let us do. Now, synchronous motor performance under different load current conditions. Now, motor is ready to take the load. Now, load increased on the motor, what will happen? Now, this is a synchronous motor as you know, and equivalent diagram, this is the diagram. So, you have to remember one thing. In case of DC, the back EMF developed in the armature due to EMF induced in armature itself, that is equal to applied voltage minus back EMF developed in the armature is the difference of V minus EB, the resultant voltage. Whereas in case synchronous motor, the back EMF induced in the armature, that is in stator, due to the flux of rotor. Due to the rotor flux, an EMF induced in the stator, that is known as the EMF. That EMF always opposes the applied voltage V. So, we can say this is a back EMF EB. So, now applied voltage is opposed by the EB, that is called V minus EB, that is equal to resultant voltage ER. That ER is equal to armature current into synchronous impedance IA ZS. Now, you can see once again. So, this is a physical diagram, stator and rotor, and on electrical analysis purpose, this is a stator and this is a rotor. Now, based on this one, once motor is running under normal condition, if DC supply, for example, if you are giving for example, if this is a 220 volts excitation. Once if you are giving the 150 volts is given, what will happen? If 200 volts is given, what will happen? And if 250 volts is given, what will happen? So, we are going to analyze this thing. Okay. So, by giving the excitation under normal condition, for example, 220 volts is given under normal condition, what is the significant changes takes place in the motor? If the voltage reduced from 220 to 150 volts, what is the performance of the motor? If more than 220, that may be 280 volts is given, what will happen? The changing input excitation to the rotor through the slip rings, the performance of stator, that the armature current, it's a power factor, how it changes, we are going to observe in this class. Now, the synchronous motor can be operated in different modes such as lagging power factor. That means here, so whatever the DC supply is given under voltage. For example, here we are going to the 220 volts normal voltage. Now, I have given only 180 volts to induce rotor poles. At that condition, this motor works on a lagging power factor. That means the current drawn from the supply is IA is in lagging with the applied voltage. So, applied voltage versus armature current, what will happen? This current is always lagging with respect to the applied voltage. That situation is known as the under excitation of synchronous motor. Now, second case, leading power factor. Now, in this case, now what will do? So, in this case, the DC supply, instead of 220 volts, I am going to give the 250 volts more DC voltage. At that condition, the armature current IA is leaded by voltage corresponding input voltage by some angle, that is the power factor angle. This situation is known as the leading power factor over excited. The current drawn from the supply in the form of leading power factor. Simple, by injecting the DC supply to our rotor. So, what will happen? So, once it is a armature current is a leading and other motors connected to the same supply, the lagging power factor, this leading power factor and the lagging power factor, overall the power factor of the system increases. That is why the synchronous motor is used in industrial purpose to improve the power factor. Now, in third case, unity power factor under normal excitation. Now, in this case, I will give the DC supply only to 20 volts. Then it will draw the what is the armature current. The armature current is in phase with the applied voltage. That is equal UPF, unity power factor. So, these three conditions I am going to perform on my DC, on my synchronous motor. So, during this period, what are the significant changes takes place in our terminology, back EMF, resultant voltage ER, armature current, we will see. Now, the equivalent circuit of synchronous motor. So, you know that this is the stator and this is the rotor. Okay, this is the rotor. The stator has armature resistance, leakage reactance and synchronous reactance. Both are we call the synchronous reactance. And so these two are synchronous impedance. Now, let us analyze. Now, what is happened here? Now, when supply voltage V is applied, here due to the ZS stator, the current is passing IA armature current. This is the back EMF EB. This is the back EMF. Now, what is the equation? Applied voltage V is equal to, here voltage is the some voltage that is known as the IA ZS, voltage drop, plus here is one source that is equal to EB. Now, applied voltage is equal to vector sum of this is equal to drop. We can say this is known as a resultant IR. ER plus EB, we are going to get these equations. So, that is the applied voltage, 3-phase voltage is equal to IAZS drop plus EMF induced in the armature EB. So, this terminology already you know. Let us, the V is equal to supply voltage for phase. Here I am going to analyze the motor for phase. So, each and every value converted to the for phase. Now, EB is a back EMF induced in the armature for phase, armature current for phase, whether it is connected star or delta, and synchronous impedance ZS is equal to RA plus J of XS. Now, theta is equal to tan inverse of XS by RA, that is the internal angle or impedance angle. So, tan inverse of XS by RA. Now, impedance drop for phase is equal to ER. ER is equal to armature current into synchronous impedance. Now, in first case, in this case, the power factor is lagging under excitation. That means here DC supply is given to my rotor poles less than terminal volt, that is equal to, instead of 220 I am giving the voltage of 180 volts only. In this condition, as we know that the back EMF induced in the stator also reduced. The flux reduced automatically back EMF also reduced. This back EMF is very less as comparing to the voltage. Here applied voltage is called V. Back EMF developed is called EB. Now V is greater than the EB condition under excitation condition. During this period, it will draw the current from the supply IA under lagging period. That means the V, this is the voltage V, the current is the IA, this is called power factor angle, lagging period. At that condition, what are the significance values? Let us do. Now, this is the diagram, you know this very well, and the phi is the power factor angle, and alpha is the load angle, and theta is the internal angle, that is tan inverse by xs, this angles here. Now, during this period, what will happen? So, let us will draw once again here. Here lagging power factor. Now, this is a, so once again because vector diagram is very important if you are understood well and good, otherwise there is a possible to confuse. Once again I am giving this one, this is a reference one, and this is a voltage V at phase angle, reference angle, and this is the applied voltage V. Now current IA lagged the voltage by due to the lagging, the over under excitation only 180 volts is given, then the current is a lagging. So this current we can say here is a current is a, the current is lagged by voltage some angle, that is called power factor phi. This is called IA. Now due to the armature current, due to the excitation here, it produces a voltage that is called back EMF voltage. Due to the back EMF voltage, due to the rotor retardation, and it is some angle from this one, this is a alpha, this is equal EB. Now we know that a resultant, this voltage, so as we know that what is a V minus EB, this is a resultant voltage. The vector difference of this voltage is equal to this voltage square plus this voltage square. We are going to get the voltage that is equal to resultant voltage. This resultant voltage is having angle of theta with respect to the armature current. Okay, so this is a diagram we are going to get under excitation condition. Here armature current is lagged with respect to the voltage, at the same time it is lagged with respect to the resultant voltage. The theta is a nearly constant value, and alpha is based on the load on the motor. Now let us see this one. Now this is a diagram, voltage, and this is a alpha. Based on this one, EB is drawn, and the vector difference of EB and V is nothing but, so we are going to resultant voltage ER, that is the theta with respect to armature current IA. Now this is a power factor angle between the voltage and armature current is the phi. So same vector diagram we know. Now applying cosine rule, here you require the two rules. One is the cosine rule, another is the sine rule in three cases: under excitation, normal excitation, over excitation conditions. Simple. What is the cosine rule? Cosine is the two vectors. We are going to algebraic sum of the two vectors, adding this one. Sine vectors, sine rule. So opposite angle into the side, we are going to sine. So by applying the cosine rule, applying the sine rule, we are going to get the alpha as well as we are going to get the ER, resultant voltage. Our aim is to find that ER as well as a sin alpha. Now applying the cosine angle, now here what will happen? So here I am going to find that EB here. So here you can see it. So this is nothing but this and this are same. So this is equal to, we can write the EB, and this is nothing but V. We can write V. So I am going to find that this is equal ER. Based on ER, based on this one, I am going to find that this EB now. Okay. So once again, I am going to find this is equal to EB. I know this is equal to V based on the supply voltage. V I know from the supply. ER I can know because what is the ER? ER is equal to, I can write it, ER is equal to IA ZS. ZS is the synchronous impedance, IA is the armature current. If you know the armature current, if you know the synchronous impedance, I can find the ER. And from the input voltage I know the V. From ER and V I am going to find that what is the back EMF induced in the stator, I am going to find in cosine rule. Okay. So let us see. In triangle, this is the O, here you can see O, A, B. This is equal to EB. I want to know that EB. I know the ER, I know the V based on applying the cosine rule. So EB square is equal to V square applied voltage whole square plus E square 2 vector, this is whole square, minus 2 into this vector and this vector angle between these two. What is the angle? Now you can see that, don't confuse here, this angle dominates. So here you can remember the angle between the ER and V. Now total angle is the corresponding, you can see total angle is equal to, this total angle is equal to theta, but this angle is equal to phi. I want only this angle between the two voltage sources. That means total theta minus phi, I can write the angle between the two vectors ER and V. Same thing I applied here. So what is the cosine rule? Cosine rule is the vectors, sum of the two vectors. So EB square, back EMF whole square is equal to voltage whole square plus ER whole square minus 2 into V into ER into cos theta minus phi. Okay. So that is the one equation. Now based on the equation, now EB is equal to under root, we are going to get this one, B square plus ER whole square minus 2 into V, same thing. Now EB we found by using these two equations. Now apply the sine rule. In cosine rule, what we have seen, in cosine rule, by applying this vector we find EB. Okay. Now in sine rule, now we are going to find that, so this side opposite angle and this side an opposite angle here. Okay, once again you can see it. So here we are going to get, what is this V, this is a E, and we are going to get that this is the angle, this one. Okay. Now what is happening here? Nothing but this alpha is nothing but this is the alpha, because this one is equal to this one, same alpha, this is a reference to this alpha. So this is, we can write the alpha. Now what is the angle here? So I am going to get is theta minus phi. I am going to get this one. You know this angle, we know this angle, we are going to assume this one. Then I am going to find that. Okay, so I am going to find that. So I want this side, this is called EB. EB by sine theta minus phi. That's I can write it. EB by opposite angle sine theta minus phi. Okay, is equal to, at the same time this is a ER. So ER I can know ER by, I can write it, so I can ER, so that is equal to ER by, so okay, you can write this one. So ER by sine alpha. I want the sine alpha required. I require the load angle, alpha is required. So I can write it sine alpha is equal to ER sine theta minus phi by EB. Hence the load angle alpha can be calculated once EB is known. From cosine angle we are going to write EB with the help of the V and resultant vector, and with the help of the sine rule we are going to find that alpha. These are the two things we are going to find. Once again, under excitation condition, the alpha and theta and phi as per their significance, by applying the cosine rule I am going to find that back EMF in terms of ER and V. By applying the sine rule I am going to find that alpha in terms of same EB and ER. Once I know what is the ER and EB, I am going to find that what is the load angle on stator and rotor axis. Okay, so this is the under excitation condition when the EB is less than the applied voltage. In second case, same cases, same procedure. Now in this case, what when the power factor is leading over excitation condition. In this case, what we have seen, our rotor excited more DC supply, instead of 220 volts I am going to give the 250 volts over excited. Then it induces in stator EB is a more value. This back EMF induced is dominating the applied voltage under over excitation condition. Due to this one, it will draws the current input to our motor in form of leading power factor. These are the changes. When over excited synchronous motor, it will draws the armature current in a leading power factor. Once leading power factor, then what will happen? You can see, draw the vector diagram. This is a vector diagram. This is equal to, so here similar, instead of in previous cases voltage, now current is leaded by angle of phi. In this case everything is same here, EB resultant ER, now theta angle is ER. So that is a difference only. The current shifted towards anti-clockwise direction and leaded by voltage by angle of phi due to the over excitation condition. Then if leading current comes, what are the significant changes? Let us see. Now similarly, by apply the cosine rule. So what is the cosine rule? The triangle O A, B conditions. So, I am going to find that back EMF, this is called EB, with the help of voltage, with the help of ER. The vector sum of two vectors, I am going to get the EB by applying the cosine rule, that EB square is equal to V square plus ER whole square plus 2 into V into ER into cos. Now, what is the angle between the ER and V? Now, so theta is equal to up to, this is the angle, this is angle is a theta, this is a phi. I want the total angle, then sum of this phi plus theta I am going to write here only. That is the difference. Previous case theta minus phi, in this case theta plus phi only. It's the angle between the two vectors and remaining is the same. Now, so EB is equal to under square of these all formulas. Now, apply the sine rule once again. Same thing, I am going to find that. So, what is the sine? Here I am going to find that EB, the angle of this one, and ER and the angle of this one, applying this rule. So, EB by sine theta plus phi, this is the, and ER by sine alpha, but I want the sine alpha. So, that is called, simply we are going to get EB by, so what is the value? ER, nothing, sine alpha. So, I am going to get here ER by EB into sine theta plus phi, that is the formula we are going to get. So, here ER sine theta plus phi by EB. Hence, the load angle alpha can be calculated once EB is known. So, this is the analysis. Now, coming to the third case, similar analysis. Third case, what we are doing is a normal excitation. In this case, what is happened? The rotor connected to three-phase supply, stator, and the rotor is given to the DC supply under 220 volts only, and it draw the voltage V. In this condition, normal excitation, whatever the V is equal to EB, back EMF induced in stator is equal to this voltage. At that condition, we can say it is the normal excitation conditions. At this condition, it draw the armature current with voltage and angle of unity UPF. So, that is in phase angle V and I both, what is the angle between these two is a 0, cos 0 is equal to 1 UPF. So, here you can see vector diagram. Vector diagram, this is as usual voltage, but now in this case the previous cases you observed lagging power factor is this direction, leading power factor, the current is the lagging power this direction, leading this direction. Now, the normal direction this direction, only current angle changing, then automatically changes the remaining things. So, in this case, now we are going to draw, this is the voltage. Now, we are going to draw, this is the current, the voltage and current UPF. Now, as usual, this is the EB. Now, vector sum of this was equal, we are going to get that ER. Then this angle is a theta and phi is equal to, what is the value? 0. This is the alpha EB. Now, apply the cos rule and sine rule. Then we are going to get the equation. Applying the cos rule, we are going to EB. EB is equal to this whole square plus this whole square minus 2 into this value cos of angle between the two. What is the angle now? Only theta in this case. Now, applying the sine rule, this is the EB, opposite EB by sin theta is equal to ER by sin alpha. We are going to get equations, simple equations. Okay, same thing. EB is equal to V, applying the cosine rule. So EB whole square is equal to something, and applying the sine rule. So we are going to get that EB by sin theta is equal to ER by sin alpha. So sin alpha is equal to ER by EB sin theta. Hence the load angle alpha can be calculated once EB is known. So these are the basic formulas. Okay, so very easy, but you have to practice it. Now based on these things, we are going to do the problems. Before going to the problems, we require some analysis at the same time. Power equations. What are the power equations? So here, please listen here. So as we know that the motor, this is the synchronous motor, stator. It is connected to the three-phase supply. Voltage is given, and this is a rotor. Okay, rotor, and it's given the DC supply. Now, what are the power stages takes place in this one? Oh, sorry. Now, this is the stator. Stator has the stator winding. Now, three-phase supply is given, AC supply. How the AC supply converts our mechanical energy. This is how the mechanical energy is connected to the rotor, mechanical. P output. P input is the AC electrical input. How the mechanical output will come, P mech. Now, here you can remember that what is the voltage? This is the voltage. The current is equal IA. Based on input current of this machine, as we know that P input is equal to root 3 VL IL cos phi. The basic formula. So input power is equal to root 3 VL IL cos phi. At an instant you neglect the efficiency of the motor. Take the 100%. Power factor is also UPF. Now P is equal to root 3 VL IL cos phi is the input power. After input power, so then what will happen? So there is a possible to some armature losses takes place. So armature copper losses, then here some losses, armature I square RA for phase. For three phase we are going to 3 into I square R losses. Total input root 3 VLIL cos phi. In that one, some of the energy is consumed for the meet the copper losses, that is called I square R losses, copper losses. Remaining the mechanical energy PM, the mechanical energy developed in the motor is given to the rotor. Then rotor also has its some losses. What are the rotor losses? PM is coming here, that here the friction and windage losses, some iron losses takes place in this one. So what are the energy PM, the mechanical output, mechanical energy generated in the machine minus these inherent losses, so iron losses and friction and windage losses and bearing losses, all things remove it. Then we are going to get so net mechanical output, similar to the previous machines. So this is the power equations. So what are the power equations? First, input supply is equal to P is equal to root 3 VL IL cos phi minus some copper losses takes place in stator. So three phase 3 into I square RK losses. This total equal to, these are equal to mechanical energy generated in the motor. This PM taken coming from this one, some iron losses plus some friction and windage losses taken out, then we are going to get, so P net mechanical energy generated in the motor. Okay, so these are the things you remember. Now, what is the P net? Power developed for phase. Here PM is equal to, so we can write it, this is equal to, we can write directly power developed for phase or three phase, we are going to get that. So here we can write it, EB is equal to back EMF into armature current into angle between the two. Okay, let us see. That is equal to power developed PM, that is equal to here PM, power developed for phase. So here while doing the calculations, you have to convert all things into the phase values. Remember that thing. Now I am going to calculate power developed for phase is equal to, now what is the back EMF EB, what is the armature current IA, and angle between the cos alpha minus phi for the lagging power factor. So power developed in the machine for phase is equal back EMF into armature current into cos the alpha minus phi. Alpha is the load angle, phi is the power factor angle. We are going to the total mechanical energy developed in the motor for phase. Okay, so then this total mechanical energy is taken by using the equation, and this equation also we can write it, the PM is equal to, we can write it total input. What are the input, total input, what is the total input, that is equal to, we can write it for phase, and 3 into V phase I phase cos phi for phase minus I square RA copper losses, stator input minus stator copper losses. So that is a net mechanical output generated in the rotor. So these are the equal. We can write it EB into IA into cos alpha minus phi, or we can write it the input minus the copper losses takes place in for phase. This total for phase values. Then after knowing this one, so we are going to calculate. So from this one, if we are subtract the friction and windage losses and iron losses, then we are going to get the P output, motor output, net mechanical output generator. Okay, so these things you should remember. Okay, so here we are going to calculate. So if for example in the flow charts, the motor input, the motor input, so motor input is classified into the, one is the stator copper losses, and that is equal to PM, mechanical output generated in the motor, and this PM minused by friction and iron losses. Then we are going to get it P net, P out, P net, P output, we are going this one. Okay, what are the input is given here, that is dependent on the root 3 VLIL cos phi for 3 phase, or we can write the, so 3 into V phase I phase cos theta, and this copper losses I square RA, PM is equal, this minus this is equal PM, or we can write it the EB into IA into cos into alpha minus theta. From this one, this constant losses we can remove, then we are going to the output here. Okay, so we are going to calculate these things. Or for, you remember that the power developed by the synchronous motor developed for phase, so we have the very familiar formula. The PM also we can write it in the form, so PM, the power mechanical energy developed in motor is equal to, so we can write EB V divided by ZA cos theta minus alpha minus EB square by ZA into cos theta. This is a equation derived. There is no derivation for you. First, you remember that one. Previously we written EB is equal to, in terms of, so PM is equal to EB into I into cos into alpha minus theta. That is the one formula. So because we have the power is equal to V into I, power is equal to V square by R, power is equal to I square R. Similarly, the mechanical energy developed in motor to the rotor energy generated is equal, PM is equal, we can write it, so EB into IA into cos alpha minus theta, or we can write it, the perfect formula is equal, PM is equal to EB and V by ZA cos theta minus alpha minus EB square by ZA into cos theta. This formula you have to remember. So in this case, what will happen? The armature, that is if RA is neglected, because the motor reactance is a very high as compared to the resistance. Then, so if you are neglect this same equation, if you are the, so XS is equal very greater than the RA, then what will happen? So only in this formula ZS it becomes to the XS. At that condition, the theta becomes to what will have value? So theta is equal to the RA by XS, that is equal to RA, that is 1 by, so we are going to get that nearly the theta becomes to the, now so 90 degrees. Now theta becomes the unity for vector 90 degrees. Then once you are 90 degrees, we are going to apply, so cos 90 is equal becomes to the 0 value. So it becomes the 90 minus alpha, that is called sin alpha. So simple, this total equation EB V by ZA into sin alpha will gives the final equation. So we can write it, PM is equal to, so EB into V divided by ZS into sin alpha. So this is a final mechanical energy generated in synchronous motor when the armature resistance is neglected. Okay, this is a formula you have to remember. So these formulas will comes in problems. Okay, now I think you have the some idea on this one. We can do the problems in next class. Okay, so let us discuss what we have seen in this class. Okay, problems we will do later. You remember the formula, simple, nothing but it is you have to apply the over excitation, under excitation and normal excitation, the cosine rule and cosine rule. Then you remember the equations only. So what we have seen in this class, we have discussed in this period the derivation of expression of for back EMF and back EMF for phase. We are going to calculate it by using the cosine rule, the V square, that is the formula at the different conditions, and problems we are not done this problem in this class. We will do the problems next class. So I think just you practice once on paper, you may get the some idea. Okay, and thank you very much for listening my class.